Welcome back! Today we're diving into the architecture that revolutionized natural language processing, the transformer.
This is one of the most important episodes in our series because transformers are the foundation of virtually every major LLM today.
Let's start with the core innovation attention. What exactly is an attention mechanism?
Attention is a way for a neural network to focus on the most relevant parts of the input when processing each element. Think about how you read a sentence. You don't give equal weight to every word. Some words are more important for understanding the meaning.
In a transformer, attention allows the model to look at the entire input sequence and compute how relevant each position is to every other position.
Let's break down how this works. There are three key components: queries, keys, and values. These are all learned transformations of the input.
For each position in the sequence, we create a query vector. This represents what am I looking for. Then for every position, we also create a key vector. What do I contain? And a value vector. What information do I have to offer?
The attention mechanism computes a similarity score between each query and all the keys using what's called scaled dot product attention. Basically, you take the dot product of the query with each key.
The dot product gives you a single number representing how well two vectors match. A high dot product means they're aligned, a low one means they're not.
These scores are then divided by the square root of the dimension. That's the scaled part. This scaling helps keep the gradient stable during training.
Next, we apply softmax to turn these scores into a probability distribution that sums to 1. This determines how much attention to pay to each position.
Softmax takes a list of numbers and converts them into probabilities. Larger scores get larger probabilities, but everything is normalized, so it sums to exactly 1.
Finally, we take a weighted sum of the value vectors, using the attention probabilities as weights. This gives us the output for that position.
So the model is essentially asking, given what I'm looking for, which parts of the input are most relevant, and then combining information from those relevant parts.
Now, transformers don't just use one attention mechanism, they use multi head attention, which means running multiple attention operations in parallel.
Each attention head can focus on different aspects of the relationships between words. One head might focus on syntactic relationships, another on semantic similarity, another on long range dependencies.
The outputs from all the heads are concatenated and then projected back to the model dimension. This gives the model a richer, more nuanced understanding.
Let's talk about the overall structure of a transformer. There are actually two main variants: encoder only, and encoder decoder models.
The encoder reads the input and builds a rich representation of it. The decoder generates output, typically one token at a time.
BERT is an example of an encoder only model. It's bidirectional, meaning it can look at the entire input in both directions. This makes it great for tasks like classification or extracting information.
GPT is a decoder only model. It generates text auto-recursively, one token at a time, with each new token conditioned on all previous tokens. It uses what's called a causal mask to prevent looking ahead.
The causal mask is crucial. It ensures that when predicting position I, the model can only attend to positions 1 through I, not positions I plus 1 onward. This prevents the model from cheating by seeing the future during training.
T5 is an example of an encoder decoder model where you have both components. The encoder processes the input and the decoder generates the output while attending to the encoder's representation.
In addition to attention, transformers have feed-forward networks. These are just regular neural network layers that process each position independently.
These are sometimes called MLP blocks for multi layer perceptron. They typically have two linear layers with an activation function in between.
Modern transformers often use sophisticated activation functions like GLU or SWIGEU instead of simple ReLU. These are gating mechanisms that help the model be more selective about what information flows through.
Another crucial component is residual connections. After each attention layer and each feed forward layer, we add the input back to the output.
Residual connections create shortcuts that allow gradients to flow directly backward through the network. This was originally introduced in ResNet for computer vision, but it's essential for training deep transformers.
We also apply layer normalization after each sublayer. This normalizes the activations to have stable mean and variance, which helps with training stability.
Now, here's something interesting. Transformers don't inherently understand the order of tokens. The attention mechanism treats the input as a set, not a sequence.
So we need to explicitly add positional information. This is done through positional encodings or positional embeddings.
The original transformer paper used sinusoidal positional encodings, mathematical functions that give each position a unique pattern of values.
Modern transformers often use learned positional embeddings instead, or they use more sophisticated schemes like rope, rotary position embeddings, which encode position directly into the attention computation.
Rope has become very popular because it handles longer sequences better and generalizes to sequence lengths not seen during training.
There's also AI Lie-By, which adds a simple bias to attention scores based on distance, and relative position encodings that focus on the distance between positions rather than absolute positions.
Let's talk about efficiency. One challenge with transformers is that attention has quadratic complexity. Computing attention for a sequence of length n requires n squared operations.
For long documents, this becomes computationally expensive and memory intensive. Researchers have developed various solutions.
Sparse attention patterns like those in Longformer or Big Bird only compute attention for certain positions, not all pairs. This reduces complexity while maintaining most of the modeling power.
Linear attention and kernel attention methods try to approximate the full attention mechanism with lower complexity using mathematical tricks.
And there's flash attention, which doesn't change the computation but optimizes how it's executed on GPUs by being more careful about memory access patterns. This can speed up training by 2 to 3x.
Another important optimization for inference is the KV cache. When generating text autorecursively, we don't need to recompute the keys and values for previous tokens, we can cache them.
This dramatically speeds up generation. Without KV cache, generating a sequence of length n would require n times more computation than necessary.
Some recent models use multi query attention or group query attention to make the KV cache smaller and faster.
In multi-query attention, all heads share the same keys and values but have different queries. In group query attention, heads are divided into groups that share KV pairs.
So, to summarize, transformers use attention mechanisms to model relationships between all positions in a sequence. They process everything in parallel rather than sequentially. They use multiple attention heads to capture different types of relationships, and they include feed forward layers, residual connections, and normalization for stable training.
The architecture is remarkably flexible and has proven to scale extremely well. As you add more layers, more heads, and more parameters, transformers continue to improve.
This scalability is what enabled the jump from models with millions of parameters to billions or even trillions of parameters.
Next episode, we'll talk about how these models are actually trained, the data, the objectives, and the optimization process.
Thanks for sticking with us through this technical deep dive.
Until next time, keep learning and stay curious about AI.